chair. Maybe you should work. Okay, so the microphone's not working anyway, and nothing is being happy with anything today. But I
As they
think
know, spring break.
everything is recording because it's spring break. Okay.
that's
Today what we're gonna do is confidence intervals for variances and standard deviations. And isn't this like the best GIF ever? It's a GIF or GIF?
This chick killed her husband by like driving him, like convincing him, like directing him around like they were gonna go on this date, and then she drove him off a boat ramp.
Goals.
That's how she killed him in my book.
Same.
Okay, well at least it's a book. I was thinking that
No,
was...
no, it's in my
okay.
book.
Okay, that makes more sense.
The book that you didn't read, take it personally.
No, I read this one. I just didn't remember this one chick's name, and I had no idea who they were talking about. And then I was like, oh,
Let me
once I
get my
read the
mouse.
book
Okay.
part, I was like, that's what
Mass
it
is
is.
here. Okay, so first thing, why we kind of do this. So when we talk about the means, that we need to know the means are in the same like area, so it needs to be in a certain interval. We also need to know that variances and standard deviations are very small. So kind of just one example they have is when products fit together, such as pipes, it's important to keep variations of the diameters of the products as small as possible. So if we had a large variation, we could be buying like a 1/4 inch pipe and get like a 1/2 inch pipe, and that would not be okay. That would not be acceptable. That would not fit anything, and we would just all be very mad. So things like that, we just have to have very small errors. So those errors are those standard deviations. Okay, in the manufacture of medicines, the variance and standard deviation of the medication and the pills play an important role in making sure patients receive the proper dosage. Just a weird note because of this. So my brother-in-law has epilepsy, and the one thing when they started putting him on medicine was that actually like pharmacies, I don't know if you guys take a lot of pills or not, but sometimes you'll get the same medication but it'll look different. So what pharmacies do is they'll buy the cheapest drug from the cheapest supplier. So for like those generic medicines, there's you make it, but and the actual medicine that you want is the same, but sometimes what also affects you is the non-active ingredients, and those non-active ingredients can actually change between one to the other. So that's just a weird fact about medicines. So like if you have to do like certain medications, you want your pills to always be the same and from the same manufacturer, because otherwise you end up like with weird things happening. You don't want those weird things happening. Okay. For these reasons, confidence intervals and variances for variances and standard deviations are necessary. So that was kind of all the other ones were saying. Okay, so what we're going to use is the chi-squared distribution for this. So far we've used our normal distribution, and then we've used our t distribution, t-squared or t distribution, I don't know, for variances and standard deviations. Okay, chi-squared variable, so make sure you write that, is similar to the t variable, so that it's a distribution of family of curves, and I'll show you a picture in a second anyway. Based on the number of degrees of freedom, so we still have this idea of degrees of freedom. You can't really see it, so sorry. Whoops, this thing isn't working, so I've forgotten to even... It's not working at all, so that sucks. Okay, so the chi-squared distribution, it looks like a capital X, kind of scripty. Okay. One other thing, chi-squared variable cannot be negative, and the distributions are always skewed to the right. Okay, so what those actually look like when we talk about a family of curves, my mouse go again, is that there are about 100 degrees of freedom. The chi-squared distribution becomes more symmetrical. So
Chi-squared?
it's chi-squared.
Chi-squared.
Chi-squared, it really is. Yeah, I know it's gross. Same type of thing as a normal distribution in that the area is equal to 1 or 100%. Yay, basketball. Yay. Okay, so this is what the some of the family of curves would look like for this chi-squared. Is if with 1 degree of freedom, there's almost like no lip on it at all. So then like if you got out to like 100 degrees of freedom, it would actually look more like a normal distribution, and it would no longer be right skewed. Okay, so this is kind of also in your book too. So if you can kind of imagine it, that when I go to find these things, so remember we're trying to find those middle percentages. Those middle percentages, if I kind of look at this, these are going to be different areas. So if I was finding the middle thing, this little area is different than this little area. So we have to figure out, so we're not doing all of that crazy stuff because somebody's already done it for us. So somebody has already found all of these little areas and the z-scores, or I don't know if they're called z-scores anymore, that are associated with them. I guess the chi-squared score. I don't know that it has a special name at all. Okay, these are the gross formulas for it. Not too bad. Okay, it's not, it looks gross, it's not, we'll go over them, it's not that bad. Okay, I'll try to help you remember that right is on the left and the left is on the right. It's weird. So these, we're going to use a chart to find these numbers based on whatever confidence interval they gave us or give us. So n minus 1, s squared, remember that's the sample standard deviation.
What is
Over
DF?
df is the degrees of freedom.
Oh, okay. That makes sense.
Yep. So, more clicky things. Remember, this is the variance. This is our formula for variance. Our formula for standard deviation is going to be the same exact thing with the square root sign. Okay, so just think about it, and I don't even know. I mean, you could write this down, but think about it that, oh, I'm doing variance, I need to take the square root. Think about it more as trying to solve whatever it is. Okay, so it's still pretty gross looking though.
So that's just for standard deviation, is
Yep.
all of that just for?
Yep, this was variance, this was standard deviation. Same all junk inside, but different just by the square root outside.
Hey, are you going to the thingy tonight?
Yeah.
Sweet.
You guys gonna sell for a lot of money?
Hopefully. If not, I hope our stuff sells for a lot of money.
Yeah.
What is it?
5:30. Does it start at 5:30?
No, what is it?
Oh, the run a hand and
our
auction.
Run a hand and auction.
So what do you do there?
So they auction us
Feed
off
a
to
bunch of
work for
balls.
people,
Slaves.
pretty much.
Yeah, but we're not allowed to call them slaves anymore.
It's offensive to most people.
Not around here, but some people not around here, it's offensive too. Okay, so some of your questions are just as simple as, let me scroll through these thingies here. Finding the chi-scored right and the chi-scored left for a
That might
90%.
offend me.
Chi? Chi-squared left for a 90% confidence interval when n equals 25. Okay, so think about it in terms of 90%, I need to have 5% over here, and I need to have 5% over here, right? That's nothing crazy. That's kind of what we're doing. So I need 5% over here. Then this score right here is at the 95%. Okay, 5 and 95. Okay, that separated it out into 10%. Okay, so we have 10% on the edges, so 5 past 95 and 5 before the 5 score. So now what you'll have to do is you have to find your fancy book. In the table, do you guys remember where you had that T-score marked? That T-score chart marked? It's the next table.
The next one.
It is table G for you guys. In the back on page 787. And we have to, so everything we've done for the T-scores and the Z-scores, we've just basically had to find one number. So we've just been, oh, Z alpha over 2 is this number. And it worked out nicely. Now what we're going to have to do is use this table. So let me see if I have a nice picture of it. So we divided by 2 to get 5, to get 95. We did that. What we're going to have to do on this table, so what this is going to look like is I'm doing a 90%. So that told us I want the 95 and the 5. So over here I have 95 and 5. And it told us that I had 24 degrees of freedom. So I come down to 24. And I need these two different numbers to plug into my formula. Okay? So it's kind of a mess to look at in your book.
I don't mind looking at it on my.
Yeah. It's just weird. This one is just weird because we need the two different scores. Okay, and when we think about intervals,
And but it's always different numbers, or is it just those
Okay.
numbers?
yeah, so if I am doing, so the original question on the last page asked us for the 90% confidence interval.
Yeah.
Yeah, they're always different. I don't think they're ever going to be the same unless you had a very, very high degree of freedom. I don't know if I ever even actually see any the same. No, none are the same. Confidence intervals.
My goal is to be so rich that I can have my own gym at my house with a big screen TV and I can watch basketball while I play basketball. That's the dream.
We just built our building, and it's 16 foot tall, and we're so going to put a basketball hoop in there.
You told us about that.
Yeah, it's going to be pretty exciting.
That's my goal.
Maybe I need to get a big screen TV out there too. That'll be that would be creepy. Okay, so remember that 90, I need to divide that extra by 2 to get 10. I have 10 left over, 5 on the front, 5 on the back. So that's how I decide what numbers it is I'm using. Okay, now to actually solve something with that, what that is going to look like, so that you would just have to say whatever values it is. Okay, rounding rule. When you're computing a confidence interval for population variance or standard deviation by using raw data, round to one or more decimal places than the number of decimal places in the original data. Same sort of rule we've been using pretty much all along. Next thingy, when you are computing a confidence interval for a population variance or standard deviation by using the sample variance. Okay, so this one is raw data. This one is sample variance or standard deviation. Round off to the same number of decimal places. So kind of think about that. So if I have raw data, so if you have a list of numbers, let's say I have like 1, 2, 3, 4. Here, if they give me my sample information, what you're going to have is like S equals blah, blah, blah. Or X bar. I don't think they're going to give you X bar. I don't know exactly what kind of information they're going to give you. S. They'll give you S. Or S squared. So they might tell you that kind of stuff. Next thingy. This is getting really annoying because I can't click good on here. I wonder why it's not working.
Wow.
What happened? Some sort of game thingy. Okay. This question looks
Kinda
like.
just threw it up and you got hit on the hand and just like did that and shot it and hit it.
Find a 95% confidence interval for the variance in the standard deviation of nicotine contents of cigarettes manufactured in a sample of 20 cigarettes. So N equals 20. And a standard deviation, that's just S, of 1.6 milligrams. So I need a couple little bookmarky things here. So my original formula, so it's asking us about variance and standard deviation. So we need to know those. For both of those, we use S squared in our formula. I'm going to write down my formula for variance. So it is N minus 1 times S squared. This 1 times S squared over, this is the left side, so it's the chi-squared right. So if you kind of notice, your right-hand scores are actually bigger scores than your left-hand scores. I'm looking for S squared, or sigma squared. So think about it in terms of, if you divide by a big number, are you going to get, so if you divide by two numbers, one of them is bigger. If you divide by the bigger number, are you going to get a bigger or a smaller number left over? Okay, so dividing by a big number gives you a little number. Dividing by a little number gives you a slightly larger number. Okay, so right is the bigger, left is the smaller thing. So dividing by the smaller thing is going to give us the bigger thing on the right-hand side. All right, so I just wrote that down so we can use it. Our degrees of freedom is going to be 19 because it's just N minus 1. So when I go to use my chart, I'm going to have 19 in there. Now that I have that guy written back down. So now I kind of plug in everything I know. my n minus 1, so I have 19 times s squared. I'm just going to write in 1.6 squared over, I need to find that score, sigma squared over 19 times 1.6 squared, all over now their score. So my right hand one, so 95%. So on your chart, what this is going to look like is what's half of 95? Or I have 5 left over, what's half of 5? 2.5. So my one score I need to find is my 0.25 for 19 degrees of freedom. Okay, so make sure you can find, it is 32.825. That was my, where is it? That's my larger number, so that is my right hand one. It's on the right half of my table. I'm just trying to remember, give you guys little ways to try to remember it. So 32 over, or 32.852. Okay, then for the left score, I have, so the left hand tail, so any old generic thing, this is my left and this is my right side. So this is my 2.5, this is my 97.5. So then I need to go find 97.5. I'm really mumbly today. So 97.5 for 19. 8.907. Okay, so those are the two pieces. I don't know where my calculator is. The way to think about it is you have the same thing on top. If you're dividing by that larger number, this dude will be smaller. If you happen to mess up what you're dividing by or which order they're in, just make sure the bigger one's on the right-hand side after you divide. So I have 1.6 squared times 19 divided by 32.852. 1.48. What did they tell us? They told us 1.6. So because they already gave us the information, we need to round to however many they were. It was 1.48, so that's going to be 1.5. If they had given us raw data, we would have gone out to 1.4. Raw data. Stop it. I have to think about it all the time. Okay? So over here, I'm going to divide my top stuff by 8.907. Okay? So 2 sigma squared, 2, again, we're rounding to one decimal place, so you should get 5.4 or 5.5. It was 5.46. Okay, so that is my variance. Variance is that sigma squared. After you find your variance, then take the square root. So the square root of 1.5, didn't even type in my square root sign, 1.5 is 1.2. Okay, remember we're rounding to the right decimal place, the square root of 5.5 now for my standard deviation, 2.3. Okay, so these are the two types of answers it could be looking for, because it actually asks for both of them. So interval for variance and standard deviation. So you have two different intervals there.
Okay, Chasey.
Stop it.
Chasey came from.
Okay, blah, 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 blah. We already did that. Okay, did that. And I think that is the last thingy. So you can kind of see all that work there too. Okay, raw data, make sure you're typing it in your calculator in order to get the S or, yeah, the sigma. So it'll be like SX. So this guy is the only thing you can type in to get that in. Stop it. And it looks like SX, big S, little x is what it looks like.
Big E.